Okay, hello everyone. My name's Ruben, and today I'm going to be talking to you about terrain generation in Voxel slash Minecraft based worlds. This is what we're going to be building today. Um, it looks like a mess because it technically is a mess. But yeah, so before we start, there's a couple things that I just want to mention that won't be covering in this stream. That is rendering, so actually putting pixels on the screen, and I also won't be covering noise in depth. There will be a video linked in the description that explains noise specifically for terrain generation in depth, actually quite well. So yeah, let's get started. So first thing, just want to go through is explaining what this is that we're actually looking at. So this is just a flat terrain, essentially. In games like Minecraft and Terraria or whatever, they usually divide the world up into different chunks. A chunk just being a section of data that can be easily updated or manipulated without causing your system to be completely overburdened. Um, so yeah, in the game that I'm running now, or my little project here, I defined a chunk as being a 32 by 32 by 32 array of essentially just numbers, each number referring to a different type of block. So you have stone, you have grass, you have dirt, and all that kind of stuff. So what we're actually going to be doing today is taking a look at how you can put those numbers into that chunk array in an interesting way. So the way I'm doing it at the moment is pretty naive. I'm just taking the array, stepping through it one by one, and actually just filling it up. So if we go take a look at the terrain generation file, this function just takes in a chunk, which I've mentioned before is essentially just an array of block IDs. A block ID is just a byte, meaning 0 to 255. Going through that, the total chunk size, which is 32 by 32, and just filling that chunk up with the block stone. If we change this to dirt, for instance, these are all just constants, 0, 1, 2, 3, 4, and 5. You can see that our entire world at this point would just be a bunch of dirt. So how would you go about making this look a little bit more interesting? Well, the first thing you can do is just play around with the y value. Instead of making it a maximum of just the chunk size, we could make it 5. So this will go from 0 to 5, or 0 to 4 technically, and there we have a less big chunk of blocks. You can also use randomness. Just normal random function. It is noted that I'm using thread local random here. Using the actual random class built into most programming languages is not actually thread safe. There's no real difference in it, and this isn't multi-threaded, so it doesn't matter at all. But just something I added in there, since this can be multi-threaded in the future to actually make this run faster, as we'll see later on when we implement generation using noise. It can take a while to generate the entire chunk. So if I just paste this in here, this will then generate an array of random numbers between 0 and 31, 0 to 31 being the total height of a specific column. It'll just loop through that, pick a number, and then generate the world to that specific height. So if we run this, you'll see we get something that looks a bit like this, which is just chaos, actually. There's no real rhyme or reason or coherentness to this at all. It's just random numbers. There's a couple other things you can do with this as well. You can use sign, the actual sign function. We can pass it in the x value, and then we can just tell it to we can just multiply this by 100 or 32 so it doesn't overflow. And this will sort of give us a sine wave. If we actually import this. This will sort of generate the rain in more or less like a sine wave pattern. This looks more like tan, but you get the idea. You can plug anything into this and it'll make the rain look a bit different. But what we want to do is use randomness, but not randomness. How would you do that? Well, there's actually a couple ways you can do it. One of the ways is using something called noise. The one I'm showing here is called simplex noise, and essentially what it is just a way of making random numbers without generating a random number that's actually coherent or predictable. So in this case, you can actually see that this is the random noise map that gets generated, or height map. Zero white pixels being 0, black pixels being 1, and then you can do with that information whatever you want. So in this case, they used it to generate a continent. This is used in a lot of procedural generated games like No Man's Sky, Minecraft, and I think even Valhalla used this to some extent. This is also used in image processing as well, since there's a lot of different types of noise you can use. But I'm going to be using simplex noise. The only reason for that is one of the math libraries I'm using in this engine has built-in support for it, so I don't need to go write it out myself. So yeah. So to get started with, what we want to do is essentially we just want to plug in our noise into this maximum y coordinate, so that we sort of get like a more coherent terrain generation. And I can actually show an example of this running in Minecraft. Ignore all the burning trees. I was testing things. Minecraft actually does use Perlin noise to some extent to generate its world. So from this block here to this block is just a random value read from a map. These cliffs as well, and everything you see in Minecraft terrain generation is just a noise map with different values plugged into it. So how do you get started with that? Well, first off, we actually need some way to get the noise value, or to create a height map, as you saw in that image, to read from. So first thing we can do is write a function to get noise. This function right here will get you the noise value at a specific block location in a specific chunk. We pass in both the chunk and the block location, since you can actually have the same block. The block positions getting passed in are local to a specific chunk and not global to the world. So block position 0, 0 might be actually block position 0, 0, but block position 0, 1 might be like 50, 20 in a different chunk. So that's why I pass in the chunk position as well. Noise options, this is just a data class that have some information on how you define noise. Things like octaves, amplitude, smoothing, roughness, offset. These parameters actually map sort of to what you did in algebra with sine waves. So changing the amplitude might make it bigger, or changing the h value here would offset it by a couple values, b how far apart they are, and k is just up and down. So these values here are do exactly the same thing in when you actually generate simplex or complex noise. Simplex noise being what we're using here. So just import everything else. So what this function does essentially is we need to calculate where do we want to sample this noise from. So we calculate the block's x and z coordinates. So that just being which block in the chunk we currently want to get noise for. So for instance, this one might be 0, 0 because it's in chunk 0, 0. But if we go over a couple blocks, this might not be 0, 0. This might be 25 or something like that, or 20, 0 in this case. So yeah, that's why we actually just calculate the block position. It's simply just taking the block position offsetting that by the chunk position and multiplying that by chunk size to sort of move it over by whatever chunk this is. Since this number getting passed in here is just 0, 1, 2, 3 for whatever chunk we're in currently. After that, we loop through the octaves. This is all just generating the noise, so I'm not going to go into too much detail. As I mentioned before, there will be a link in the description where someone else did a video on using noise to generate terrain that explains all these values very, very well. All you need to worry about at this point is this is getting the noise at a specific location. We're using a seed to make it more random. This is like actually giving a seed to when you create the random class. So yeah, that's essentially all this is doing. So now we have a way of actually getting noise. Now we actually need to apply it to something. So to do that, this is sort of the meat of the entire Perlin/terrain generation noise thing is this entire function here. So what this does is it creates a height map for your entire world or your entire chunk. The height map being that black and white image I showed earlier, this one. So how would you generate this? Well, first off, we're going to have a couple noise option instances. This is just for actually layering noise on top of each other, since you can get some interesting results by layering more than one sort of instance of the noise on top of each other. You can think of it as blending colors to get different results, red and blue being purple. Something like that. So yeah, so this is just creating the different noise options. This is getting the actual chunk position from the one passing in. This is just a helper value, so you can actually easily reference it later, which you'll see when we're actually calling the noise add function. And this right here is the actual height map. This is just an array of numbers ranging from 0 to whatever noise gives us. So yeah, over here we're just looping through the x and z coordinates of the specific chunk, so we can actually say, since we're generating the chunk in a column order, we just care about the x and z value and not the y, since we're calculating the y at the moment. Bx and bz, this is just the block position in that chunk, which we're passing in here. This is just delocalizing it, so we can do things with it a bit later. Coordinates we'll use a bit later for actually making islands. This is rounded function which can be used to smooth out the edges of the completed noise map to sort of simulate having an island, which we'll put there. Just import power. So yeah. Over here, so we're actually calculating the noise using the different noise options. So we're passing in the block position, we're passing in the chunk position, and then also passing in the noise options we're using. And I do this 3 times, since I'm going to layer the noise on top of each other 3 times in a row using different options. So this is amplitude of 5, octaves of 4, and you can play around with these numbers a bit later to get different results. And yeah, this is also a way you can generate different biomes, since each biome can have its own set of parameters for defining how it looks. And then finally, when we're done layering the noise on top of each other, we add it into the height map. This is actually a kind of cool way of indexing a 2-dimensional array and a 1-dimensional array. So you take the column times the width of the entire row, and then adding the row to that. Doesn't really matter all that much. All you need to know is this sort of just turns a 1-dimensional array into a 2-dimensional array. Then we're adding at that specific position, we're adding in the noise map, or the noise value we generated. So now we have a height map. Now we just need to sort of apply that to our generation. And to do that, we're actually going to use another function called generate terrain. What generate terrain does is exactly the same as the one up top, where we're just naively looping through all the positions in the chunk and just filling it in. But this does something a little bit extra, which we'll see in a bit, to sort of make it look a bit better. So having like a different top block and a middle block, and having different fill block. which I'll show off in just a bit. So max Kotlin, and then the actual function that we are going to be using for generate terrain. Create terrain over here. There. So what this does is this actually fills in our chunk according to whatever height map we pass into it. So it loops through the x and z coordinates, but what it does differently is it reads the height from the height map at that specific sort of chunk column. And just to actually illustrate this, when I'm referring to a chunk column, I'm talking about this entire row. Since when we're filling this up, we're going x, z, and then generating it column by column. So this column will be first, this will be second, that one will be third, but we don't want to always have a uniform height. We want to vary it a bit. So that's why we're generating it in a column order. So you can see that this should be 8, this should be 5, this should be 7, and this value we get from the height map. This all makes sense in just a bit. This right here just sort of checks where we are currently. So if this is the top block, if it's one of the middle blocks, or if it's one of the bottom blocks, what do we want to use? So if it's less than or equal to 1, we're at the very bottom of the world, which in this case I'm just going to make sand. If it's equal to the height, so this is the very top block, then we use whatever the biome specifies as the top block being. So in this case it will be something like grass. If it's not the top block, if it's lower than the top block but it's less than the biome's depth, this is the dirt. So in Minecraft, for instance, you would have a layer of grass, a layer of dirt for 4 blocks deep, and then a bunch of stone just all the way down. This is essentially what this does. So this just defines that underground, sort of like a middle block. Yeah, and then anything else below that is stone, and if it didn't fall into any of these other categories, it means that this should be an air block, just so that we don't fill in the world with a bunch of crap. And then finally we just set that block into the chunk, this the exact same thing we're doing over here. So now if we actually use this new terrain generation in our world, when we generate the world, it should look something like this. Yeah, there we go. I will go over everything because I do realize I went a little bit fast. But yeah, essentially that's all we did was go from a flat terrain to using a texture that we generated dynamically to specify how the terrain should look. You can actually play around with these values. They're specified in the noise map over here, or when we actually create the height map. We can play around with these to get different results. So changing that to 5, changing this to 2, changing smoothing to 20. Should give us a bit more of a mountainy terrain. There we go. Now I have a bunch of tall peaks. So yeah, most of actually creating Minecraft clones is just playing around with the noise generation until you're happy, calling that a biome, and then adding 17 of them. But yeah, that's more or less everything. Getting to this point does involve a bit more work though, since there's a lot of stuff you need to consider, like actually how do you render all these blocks, since actually drawing these one by one would take almost forever and definitely set your computer on fire. So that's why what a lot of the games do is they use something called batching, where they have a single chunk and then on each face of that chunk they just check its neighboring blocks. If that's air, it'll add that face. If it's not air, it won't add that face. So if you actually go into one of these giant pillars, you'll see that you can see, or you can see through it. Um, so like that. So you can see the insides of these since they aren't getting rendered at all. But if I do dig down a little bit, yeah, the faces do get added. So yeah, that's pretty much everything I wanted to cover tonight. There's time for questions now if anyone has something they want to ask or something want me to go over again. Now's the time. I do say there's some questions in chat now. This is Kotlin I'm using. It's sort of like the brother of Java. What makes it nice is they took what made Java horrible and improved upon it. So you have things like operator overloading, um, also things like this where you can pass in functions. You can pass a function into you can pass a function as a parameter, and you can do cool stuff like this. Yeah, it's just a bit cleaner. Blending different chunks together, that's actually handled by the height map. So you'll see I'm passing in the chunk position. So because we're using simplex noise and it's sort of like predictable randomness, um, it'll be uniform no matter what value you pass it. So you won't get two completely different values if the values you're passing to it are close together. So that's how that works. Yeah, some other cool things you can do with this as well is the seed. As most of you, if you've played Minecraft before, you know you can enter whatever value you have as a seed. So the way you can actually do that, since the seed is just a number, we can actually just write a quick function here that takes in a value, takes in a string value, and the way we can convert this is a couple different ways. The easiest of which is just to ask it what its hash code is, since this will be unique for whatever string you pass into it. And it'll be the same no matter how many times you pass it into the thing. So this will turn number. I think it actually just turns, yeah, an int. It's fine. So we can use this function to get a random seed. So back in our world class, we're passing the seed. We can just call this function called getSeed, and I don't know. Any suggestions from chat? What cool seed you want to see we generate? Fun fact, actually, the one you saw now, is that word. Uh, cool. I'll use this one. Nice seed, bro. Let's see what this gives us. Yeah. Oh, that is actually pretty cool. Huh. Did not expect that. Sweet. So this is just a giant egg. Yeah, the lays a bit rough. But that's YouTube. Don't think there's, well, maybe a couple ways. But yeah. I actually really like that. See, that's pretty cool. Um, yeah, if there's no other questions, I think we can end the stream here now. So thanks everyone for coming. Thanks for watching. If there's anything, leave it in the comments. I'll probably get around to it. And if there's something I wasn't clear on, we might do something else in the future to just clarify that a bit. There's still a lot to cover in this. Some of the other interesting bits, like I mentioned, is actually generating the chunks, since that can go horribly wrong very quickly and light your computer on fire. Um, but yeah, thanks for coming. Thanks for joining Tech Tuesday, and keep an eye out for the next video.